Hi and hello everyone. What we are going to see next is the continuous time Markov chain or discrete state Markov processes, right? Continuous time discrete state Markov process, which we all calling it continuous time Markov chain. Before we go to continuous time Markov chain, first we will see a simple version of it, which is what is the Poisson process. That is what we are going to see first. So, but for Poisson process to start with, like we will start with what you already know as the exponential distribution and some of its properties, because this is more important to understand the properties first, because this is what is going to be used throughout in the continuous time Markov chain theory. In our course on queuing theory, like what we are going to see is the first at least major portion of the course relies on the Markovian models. So, and hence this is the one distribution which is crucial. So, a widely used distribution in queuing theory because of its nature and because of its connection with the Markov chains. And to get familiarized with notation and other stuff, like what we are using is this exp within bracket lambda to mean that an exponential distribution with parameter lambda, but lambda is strictly greater than 0, and the PDF is of this form is what we would mean when we say exponential with parameter lambda, right. So, this is the form lambda e to the power minus lambda x for x non-negative, of course, this is 0 otherwise, is what is the form. Since there are many different forms of this exponential distribution, so it is better that we familiarize with what is our form. So, sometimes some books would call negative exponential and so on, but does not matter. We will call simply as an exponential for this form with parameter lambda, which we denoted by exp of lambda, which has its distribution function given by this, as you know already, and the complementary CDF or complementary distribution function is basically representing probability of x greater than x is 1 minus f of x, which will be simply e to the power minus lambda x for x non-negative quantities. And its mean is 1 by lambda, variance is 1 by lambda square. Okay. Sometimes in order to make it a little bit more clear, in the general context, it will be written as exponential distribution with mean 1 by lambda. Exponential distribution with mean 1 by lambda, we mean its support is 0 to infinity and the form is this, then only you will get mean 1 by lambda. So, that is also another terminology that is used if that is convenient sometime to represent, rather than exponential distribution with mean 1 by lambda is what would be written to express this particular thing. And because of this quantity, like for the coefficient of variation for exponential distribution is unity, it is equal to 1, and that is the important one of the properties of this exponential distribution. And for us, right, in our analysis, in our queuing systems, this random variable would represent the quantity of time, and the parameter lambda would then represent a rate that has units of events per time. Okay. So, sometimes this is also called rate because of the interpretation that one does here, because whenever this represents quantity in time, the time for example, for the time between two arrivals, time it takes to serve a particular customer and so on. So, it is representing time, and in that case lambda would represent the rate, that is what you. Now, for a continuous positive random variable x having distribution function f x and the PDF f x, the failure rate or hazard rate, it is d actually, hazard rate function is defined by r of t, it is f x t divided by 1 minus f x t, because we know what is f x and what is 1 minus f x and what is small f x, right, for the exponential. So, for the exponential case, this will be a constant. So, the constant hazard rate function would represent the exponential distribution case. What it does is that it helps us to compute the probability that there will be a failure by time t plus delta t, given that there has been no failure up to time t. So, that is what this quantity will help us to compute, right, and that is what you would see later. Now, this exponential distribution satisfies this property that is given here. What does that mean? That the probability that x is greater than t plus s, given that x is greater than t, is simply equals to probability of x greater than s for any t s greater than or equal to s. Okay. Since the right side what is it? It is e to the power minus lambda s for an exponential with parameter lambda. The left side you can write down the quantities, numerator, denominator, like this is probability of A given B form. So, probability of A intersection B divided by probability of B, right. So, you write it down and see that this will also be e to the power minus lambda. So, you can check this easily, and this property is what is called as memoryless property, and again an exponential random variable satisfies this memoryless property, and it can be shown that the exponential distribution is the only continuous distribution with this property. The only other distribution that has this property is the geometric distribution, which is the discrete analog of this exponential distribution. So, what it tells, suppose if you are looking at in terms of the context of our queuing context. So, the fact that suppose an arrival from the previous arrival to time up to now, like if it is time t. So, if this is there is no arrival, then what is the probability that this will be the arrival will happen after s time units from now. The current time is t, that if you think it. This will be same as if you are starting it is from this time, and the probability that the arrival will happen after s time units, right. That is what this would represent if you have to put a context on this particular case. Okay. Now, to understand or to appreciate this memoryless property a bit more, let us look at this figure that we have here, and okay. So, let me just highlight this portion alone a little bit, right. So, this portion alone a bit to see what we mean here actually, right. So, look at this graph. Of course, all exponential distributions will be having a pattern of this form when you draw the PDF of an exponential distribution with parameter lambda. Now, here we have taken lambda to be 0.5. So, it starts at 0.75 and then it will decrease to this, right. That is how the typical pattern would be this, right. Now, so this curve would be the lambda times e to the power minus lambda x. Now, if I pick an x naught, okay, if I pick an x naught, and if I look at what is the probability that this probability where my t is my x naught. So, x naught plus x is what then you are looking at it further, then that would the conditional quantity would be, right. So, basically if you have passed up to time x naught, and if you are looking at that, means that the future is essentially this portion, right. The future is essentially this portion. Now, in order to make this as a genuine density function, you have to scale it by the area of this one, which is essentially e to the power minus lambda x naught, right. So, if you do that, then the function that you will get is this, and if you plot this function will be like this, right. This is what you will have it here. This is the curve. Now, this blue colored curve and this red colored one is exactly the same, except that this has shifted by this much time unit. Okay. So, the tail, when you magnify it, right, when you magnify it, has exactly the same shape as you started it here, right. This is what essentially the left side would be, right. So, this is what is the question that you are looking at it. So, the exponential distribution is the only distribution, only continuous distribution that has this property, that its tail, when you magnify it, would exhibit the same behavior as the original one when you are starting original distribution, right. So, that is what you will see with respect to an exponential distribution, and this is the only distribution that with this property. Okay. This plays an important role in Markov analysis. So, there will be many characterizations. Of course, memoryless property is one because you can think that this is the only one. When you show that, okay, that is what it would mean. And x has an exponential distribution if and only if this one. What is this? Expectation of x given that x is greater than y would be y plus expectation of x for all y, right. You can intuitively you can understand this must be true because of this memoryless property, because it does not matter whether you have crossed up to time y, the expectation, because the distribution is going to be the same. So, the expectation is going to be the same. So, it is simply adding up to y plus expectation of x, the original one, right. Or you can think that expectation of x minus y given x greater than y is expectation of x for all y. That is what you can show it here also. So, this is one characterization. The other one is, there are many characterizations, but these are couple of things which might be of some help at some point of time. Two independent continuous random variables x1, x2 are exponential if and only if the minimum of those two and the difference of those two, they are independent. This is another characterization of exponential distribution. Now, let us look at some more properties. You also know that Laplace transform of its density function or the Laplace transform of its distribution function, in this case both will be one and the same, because this is a continuous random variable with a density, and that will be equal to lambda by s plus lambda. You can connect this to MGF characteristic function, right. Now, if x1, x2, xn, they are all IID exponential lambda. So, they are all of them are exponential with lambda and they are all independent. Then their sum is basically a gamma random variable with parameter n and lambda, where gamma n lambda would have this particular form, right. When you n equal to 1, you would see that this will be simply the exponential distribution. Now, for n equal to 2, it is lambda square times x e to the power minus lambda x is what then you will get, that is gamma with parameter 2 and lambda and so on, right. So, that is what you will get. The sum of IID exponentials is gamma, that is what you need to remember. And if you have independent exponential lambda i's, right, it is not IID, it is they are just independent, these are n random variables are independent, then the minimum of these xi's would be exponential with parameter summed up, okay, with parameter sum of lambda I. So, this is also an important property. All these properties is what we will be using it, we will be seeing it. So, this is independent, then the minimum, right, you can use the functions of random vector, right, these n random variables to show that this is an exponential with parameter this. So, for minimum and maximum you have an easy way of showing it, finding its distribution. So, using that you can easily see that. So, for example, minimum is greater than x, some particular quantity, some t, which means each one of them is greater than t. So, the joint product you will get immediately the corresponding distribution, which will show that exponential is sum of lambda. Easily you can show that. Okay. Similarly, these are independent with exponential lambda I, then the xi is equal to the minimum one, the probability is given by lambda I by summation of this lambda j's, right. So, the minimum, as you know, is distributed as this. So, essentially what you are looking at is xi being the minimum. Suppose if two random variables, suppose if you are looking at it. So, x1 will be equal to minimum of x1 and x2, which is same as probability of x1 less than x2. That is what it would mean. So, that is what will be equal to this quantity here, right. One can directly show it or easily for 2 and you can extend it for n using these properties and so on. Suppose maximum of 2, at least we would need it. So, if x1 and x2 are independent exponential random variables with parameters lambda 1 and lambda 2, then the CDF of the maximum of x1 and x2 can be obtained to be this. Again, maximum you have easy way of computing its distribution function, use that to get to this distribution function, right. So, this is the distribution of the maximum. So, minimum is exponential, but maximum need not be exponential, right, and if that will be following this particular thing, that is what you would see here. Okay. some more properties, that if you have x n independent exponential lambda I random variables, then a mixture of them having the PDF of that mixture is given by this, where the mixtures are according to this quantities AIs are non-negative and they sum to 1. Okay. So, it means in some proportion, if this is lambda I times, it will take this particular the ith one xi, with other proportion it will take the other random variables and so on. So, this is a mixture, this is what you call a mixture of distribution. So, this particular mixture is what is called as n stage hyper exponential distribution and denoted as Hn. So, exponential distribution ke liye, like we will be using it m, right. So, Hk or Hn would mean that it is the hyper exponential distribution, which is nothing but mixtures of independent exponentials. Okay. As opposed to this, you could also have this kind of distribution. When you have independent, where lambda I not equal to lambda j for I not equal to j, then the PDF of their sum, okay, PDF of their sum is given by this expression, where this Cin is exactly given by this expression. Okay. This is called the hypo-exponential distribution. So, the first one is hyper exponential if it is simply a mixture, which is you can think that this the particular random variable here takes the value xi with probability ai. You can think of these ai's as probabilities. Here it is a sum, that is what you are getting it. So, you will get this. It might look like this and this are the same form, where this Cin is given by this, right. But this is not a mixture, it is essentially like it is given by this particular form of this. So, that is what it arrives. It turns out to be the case here, but whereas this one, sometimes this hyper exponential is also called mixed exponential, because this is a mixture of them. Okay. Now, if you want to see the representation, right, the coefficient of variation of this hyper exponential is always greater than 1, one can show, and it is always less than 1 for a hypo exponential, whereas it is exactly equal to 1 for an exponential distribution. So, whenever you have a model where this is being exhibited, you can think of which distribution to pick from the family of exponentials, like are related to exponentials. One can think of hyper exponential and hyper exponential, because the coefficient of variations is this is one is greater than 1, the other is less than 1, and the third one is equal to 1, which is exactly for exponential distribution. Now, if you look at here, like hyper exponential corresponds to n stages in parallel, right. So, you can think of this hyper exponential as if some stage, say 1, 2 and so on, n are there. So, you are picking one of these, say this is with a1, this is with a2, this is with an and so on, and then you are getting it done, right. Whereas, in this particular case, it is 1, 2, 3 and so on n. So, it is basically you are summing through all of them. Okay. So, you will exit, or you will come here, you will exit here, you will exit here, you will come here and so on, whatever. You can think this kind of situations where hyper exponential corresponds to a system in parallel, and suppose if you think about customer arrives and he will get servers from any one of these servers, and he will pick the servers according to this probabilities a1 and to an, and then he gets served and he leaves. So, what is the the distribution of his service time is what would be given by this. Whereas, in this particular case, he will get service from here, and then he will go to get service from here, and then service from here, and then service from here, all this as a sum. That is what represents the sum, is what would be given by this kind of situation. So, hypo exponential corresponds to something which is in series, and the hyper exponential corresponds to something which is in parallel. That is what the mixtures would be, and this is what is the sum would be in this particular case. This distribution also plays a critical role. Of course, we will see much more general distributions than this, which is again related to exponential in some form, but these are the immediate neighbors of exponential when you are trying to expand it to slightly more general situation that you have. Okay. So, this is about exponential distribution and its properties. Now, what we will now do is we will define what we call a counting process. Okay. So, a continuous time random process, which is n of t is what we are denoting it is said to be a counting process if this is the number of events occurred from time 0 up to and including time t. Right. For a counting process, we will assume that it is basically n of 0 is 0, so it means at time 0 your count is 0 and it takes values in the set of all non-negative integers, and nt minus ns for s less than t represent the number of events that occur in the interval s to t. So, a counting process is a stochastic process with state space as the set of all non-negative integers, and that starts at 0, and it has as the time progress the state only increases, right. That is what we will come out to be here, because it is counting the number of events, so called what we call whatever we may define as event. So, that is the number of events it is counting. So, it is a counting process is what then you are looking at. Say for example, if you look at the number of persons who enter a particular store up to time t, if you look at it, it is a counting process, because starting from some time point, maybe if you are looking at a store which opens in the morning, so that is your time 0, right. If you are looking for one day, suppose if you are looking for a month, then the beginning of the month and the first day of the month, that is time 0. So, whatever it is up to time t, no matter how you are defining t. So, the number of persons who enter a particular store up to time t, this word up to is important, is counting process. Then total number of people who were born up to time t is a counting process. The number of persons in a store at time t, this is not a counting process, right, because this can go up and down, because this is at a time, it is not up to time, this is not a counting process, right, you can see. Now, a counting process is said to have independent increments, right. Look at here, so this is what we call it as nt minus ns is the increment of the process in the interval s to t, right, nt minus n, this is what we call it as the increment, and it has independent increment, means that in non-overlapping intervals the increments are independent, right. That is, for any t1, t2, tn, the random variables nt2 minus nt1 and nt3 minus nt, the increments, they are all independent. So, such a process is called as a process with independent increments, and as similar to this, like you will also have a process with stationary increments if this increment in an interval from t to t plus s depends only on s and not on t. So, it means that over a time point, right, where the interval is placed, here the interval is t to t plus s, where the interval is placed is not relevant, only the length of the interval is relevant. So, this is said to have stationary increments if the distribution depends only on s, not on t, then it is said to have stationary increments. Okay. Now, with this definitions of basic 3 processes, like we will try to see what is a Poisson process. So, this Poisson process, which is one of the most widely used counting process and is used wherever you are counting occurrence of certain events and that appears to occur at a certain rate, but what is important is completely at random. If it is something happening in a deterministic fashion, that every 1 hour one customer comes or every 1 hour one comes, that is not really a Poisson process model, but something that occurs completely at random without any structure, then that is a scenarios where this Poisson process could be a potential model to represent that behavior. Say for example, the number of car accidents at a site or in an area. Suppose if you are looking at a particular stretch of a road and then you are looking at the number of car accidents, okay, in that whole area or in a particular spot or whatever, okay, the whole stretch could be considered as one site, right, and then you could think that how many accidents can happen. So, probably for example, you may think that there are 2 accidents happen per day on an average based upon the last 1 year data. Suppose if you think so, if you have that information with you, but the accidents may not happen at a particular time on all days, or right. So, it can happen any time during the day. So, then you have a scenario where a Poisson process could be a model, because the accidents can happen randomly during that period. That is what you are looking at here. Or the location of users in a wireless network and the request for an individual documents on a particular web server. So, the outbreak of wars, photons landing on a photodiode, arrival of customers at a post office, and so on. Like there could be a number of situations where, and it has been shown using empirical studies that when you have large number of unknown sources from which the arrivals can happen, or the incidents can happen, the events can happen, then the superposition or all these things put together would behave more or less like a Poisson process is what has been shown in the literature, right. So, it is a quite good approximation for most of the situations, and it is a quite good first cut approximation, if I have to say so, because you are extracting the very fundamental property of randomness only through this Poisson process, right. And once you get, then of course you can improve upon these models further. Okay. So, in that sense this serves as a first model for many situations. So, what is a Poisson process and how do we define a Poisson process? A counting process is said to be a homogeneous Poisson process with rate lambda or intensity lambda, which is strictly positive quantity, if it starts at 0 and it has independent increments, and the number of events in any interval of length t has a Poisson distribution with parameter lambda t, or with mean, a Poisson distribution with mean lambda t. Okay. So, this is what is called a Poisson process. We are calling it homogeneous because the parameter here is independent. It is basically the rate or intensity of the events to occur according to this particular process. Now, we are assuming that to be a constant rate. Of course, this is only an approximation. Whenever that is there, you tend to say this as a homogeneous Poisson process. Okay. It starts at 0 because it is a counting process. So, it is at time 0, it is no event is happening, then the events start to occur, and it has independent increments, which means the increments in non-overlapping intervals are independent, and the number of events in any interval of length t has a Poisson distribution with parameter lambda t. This homogeneous Poisson process also has stationary increments we can show. Of course, sometimes this is also given as part of definition, but one can also show from this that it has stationary increments in this particular case. So, this definition then fixes all finite dimensional distribution of the stochastic process, because like if you want to know completely about a stochastic process, you know that you need to know the finite dimensional distribution. So, in this particular case, this definition fixes all the finite dimensional distributions of the stochastic process. Now, you also fix a particular time which is strictly greater than 0, which is capital T. Now, define a new process n suffix t by n suffix t of t as n of t plus t minus n of t, right, where this n is the original Poisson process. This is Poisson process. Okay. Now, what I am looking at it, I am fixing a time and I am looking at the process or the increment of the process from time capital T up to time capital T plus small t, right. If I look at this and if I define this as n suffix t of t, then this is again a Poisson process with rate lambda. So, what does this mean is that the Poisson process probabilistically restarts itself at any point of time, and this is the essence of Markov property, right. So, you have a timeline, right. So, the process whether starting at 0, so you have observed up to time some particular time, and you want to look at the process from this particular time into the future, like So, that means the past has no bearing. So, from this point onwards what you look at it, this will be equivalent to what you would have looked at from the beginning, from time 0 up to now, right, and going into the future, right. That is what it is. So, it is any time is as good as starting time, right. So, any time is basically the process restarts itself in a probabilistically, right. So, that is what is the Poisson process property, and that is what the Markov property in a sense. So, this Poisson process is also satisfying this. So, that means this process would be again a Poisson process for a fixed capital T. Okay. Now, as an alternative definition, of course, there are different definitions that one can give, like we have exactly same accounting process, homogeneous Poisson process with rate lambda. If n of 0 equal to 0, it has independent increment. Instead of this property that we have set, the number of events in any interval of length t has a Poisson lambda t distribution. You give this property where you say that probability of one event between t and t plus delta t is basically lambda times delta t plus order of delta t, and 2 events is equal to order of delta t, 3 events order of delta t, and so 2 or more events, it is basically the union itself is order of delta t, means that there will be probability of 0 event. Then from here you can write it down, say as 1 minus of lambda times delta t plus order of delta t, where this notation O of delta t, order of delta t denotes a particular quantity that becomes negligible when compared to delta t, as delta t tends to 0, which means that it tends to 0 faster than delta t. That is what it would mean, right. This limit is what is meaning actually. Okay. So, basically this is called the orderliness property, that or regularity property for the Poisson process. That is what is this means, probability of one event, since this is stationary increment things, like up for where is this t is located does not matter, right. It is only t delta t that relevant. So, that is how it is coming out to be lambda times delta t, and this is order of delta t, and 0 event is 1 minus lambda times delta t plus order of delta t. Now, with this definition, which is easier here, starting from the basic principles, obtain the differential difference equation satisfied by the state probabilities of the Poisson process, right. N of t is a Poisson process, it is a counting process. So, its state space is 0, 1, 2, 3 and so on. So, you want to look at probability of n of t equal to particular to determine the distribution at a particular time t, and if you denote it that by p and t, you can show that this p and t satisfies this differential difference equations. This is differential equation because it involves derivatives, first order derivatives. It is difference equation because this involves Pn and Pn minus 1. So, this is a difference equation. So, this is a differential equation, and you can solve this and show that n of t is actually equal to Poisson lambda t distribution. So, that you can show that this alternate definition implies the previous definition. But what is our interest? Not showing this particular thing, but the way of how one arrives at the differential difference equations satisfied by the state probabilities in a continuous time Markov chain in general, and in this particular case is a Poisson process. So, you need to understand that process very well in order to understand the Markov chain process completely, and then one can look at how one can solve this once you get this. So, this is a already, like the n of t follows Poisson lemma distribution, that is what is already given in the definition. This is alternative definition. By showing equivalence between these two, you will do this process that makes you familiar with the process of how to obtain this kind of differential difference equation satisfied by the state probabilities in a general setup as well. So, this will give you a stepping stone. So, pay attention to how we are doing this into this case. Okay. This is an exercise you can do, but let me also give a hint of few steps how one can do that. Okay. Now, consider first P0 of t. This is a border state, this is a boundary state. So, 0 is a boundary state. So, correspond that means that what? Probability of n of t equal to 0 means by time t there are only 0 customers in the system, or the system is the process is in state 0 by at time t starting from 0, which means 0 to t there is no event has happened. That is what it means. That is the probability of no event by time t. Now, look at in an interval after t plus delta t, up to t plus delta t, what would be p naught of t plus delta t, you look at it. This can happen in this way, that probability of 0 arrivals into t. So, what you are doing here is that you have 0 here, you have t and you have t plus delta t. This is a timeline that you have here, right. So, there is 0 arrivals here and 0 arrivals here is what you would have. Now, by the independent increment, this probability is independent of this what is happening in this interval, right. So, that means this is equal to probability of 0 arrivals in 0 to t multiplied by probability of 0 arrivals in t plus delta t. Probability of 0 arrivals in 0 to t is p0 of t, and probability of 0 arrivals in t to t plus delta t, the 1 minus lambda time delta t plus order of delta t or minus order of delta t, does not matter, right. So, that is what you have here. This is what it is. Now, what you do, you keep this and you take this 1 times p0 t the other side. So, the right side you will have minus lambda times delta t plus or minus order of delta t multiplied by p0 of t. Now, you divide by delta t and take limit delta t tends to 0 to get the left side will become p0 dash of t or d by dt of p0 of t, and the right side you will have minus lambda times p0 of t, and this one would tends to 0. So, this is what is the differential equation that you will get. This is a simple differential equation, linear, whose solution is you can obtain it some constant times e to the power minus lambda t. The constant will turn out to be 1 because of this property, right. What is the initial condition for this differential difference equations? P00 of 0 is 1 and Pn0 is equal to 0 for all n greater than 1, right, because the process starts at 0. That is what this means. Okay. Now, using this, the solution is P0 of t is equal to e to the power minus lambda t. You have obtained it. Now, for n greater than or equal to 1, we can consider in a similar way. This is what is important, the argument. Pn in an of t plus delta t, which means there is system is in the process is in state n by time t plus delta t. This could happen if I break this interval into two portions, 0 to t and t to t plus delta t. It can happen in this following way, in the following mutually exclusive way, right. N arrivals in 0 to t and 0 arrivals in t to t plus delta t. N minus 1 arrivals in 0 to t and 1 arrival in t to t plus delta t. N minus 2 arrivals in 0 to t and 2 arrivals in this, and so on, going up to 0 arrivals in 0 to t and n arrivals in t to t plus delta t. Now, you know this one again by the independent stationary increment property, what happens in this interval is independent of what happens in this. So, this probability is multiplied by the it becomes product. So, Pn of t, probability of n arrivals in 0 to t and 0 arrivals in this interval is given by this one, right, 1 minus lambda time delta t minus order of delta t. N minus 1 arrivals and 1 arrival is basically this multiplied by lambda times delta t plus order of delta t. This one is n minus delta t and 2 or more arrivals, you already know it is order of delta t. So, all of these are order of delta t you will have. Now, again you do the similar process, that p and t you take it to the other side, you will get this. So, this side you will get this expression plus some order of delta t, because you can club all those order terms, right. Now, you divide by delta t, take limit tends to delta t tends to 0, you will arrive at this particular differential difference equations, right. That is what is important. So, this is the kind of argument that you will use to arrive at this kind of differential difference equation, even for in general for a continuous time Markov chain. So, the argument here is a stepping stone. So, this is how you arrive at this particular equations that you will know. Okay. Now, we already showed that P0 of t is e to the power minus lambda t. Now, what we do for n is equal to 1, this equation is basically equal to this. We already know this. So, this is what it is. So, this is again a differential equation. If you solve, you will get this, but this is capital C here, capital C, because I am using capital C here, or here it is small c, whatever it is. This C and this C is one and the same. Now, using this gives us this C is equal to 0 and hence P1t is this. Now one can use the method of induction, because you have shown now base case 0 and 1 also satisfies this. So, you can assume it for n minus 1 and then you can show that this to be true for the nth one. So, by the method of induction it can be shown that this is equal to this. So, basically the state probabilities follow a Poisson distribution. Now, as an alternative, which is again you need to pay attention, because sometimes this may not work. So, you may have to use this kind of technique. So, we are just trying to know more techniques or more methods to analyze equivalent, because some one or other may be helpful or may be easier to use in a particular situation. That is the reason. Now, what you do here, you are defining the state probabilities. You define the probability generating function of these state probabilities at time t, okay, which is is basically expectation of z to the power n t is what this quantity is, right. Now, you have this differential difference equations that we have seen here, right. So, basically this one and this one, right. You multiply this by z to the power 0 and you multiply this by z to the power n, and sum and derivative and everything, if you look at it, right, you will arrive at this PDE. Of course, this is actually only like with respect to t, the derivative is there, but still it is partial differential equation. But solution of this, and what is the initial condition? The condition is probability of z at 0 is 1, is what then is the condition, right. The PDE and along with this condition gives you this. Again, this is some constant times e to the power this quantity, where this is equal to 1. So, this is what you are going to get here. Now, this is what you have here as the probability generating function of the state probabilities. Now, you know what is this e to the power minus lambda t, you can take it out, and e to the power minus lambda t times z, you can express it as a power series and take the coefficient of z to the power n to arrive at this quantity, right. So, this is another way of doing it through generating functions. Once you obtain the method of induction is one way, generating function is another way. At least two methods then you be familiar with, so that you can use any of them depending upon the requirement. So, in this particular case you would need the theory of little bit of differential equation ideas to see. Of course, we are assuming calculus knowledge, so obviously this is doable in some sense. Otherwise, it is not a big deal, because you can always use the basic ideas that you will have with respect to differential equation. You will have alternative methods always. Okay. So, let us stop here and we will continue in the next lecture further properties of this Poisson process. Okay. Bye.